This is Math 432, Applied Combinatorics. I'm Professor Asaf. Today we're going to be talking about choice. So this is a definition. A lot of people think this is something that we prove, but here's a definition. This symbol, which we read as n choose k, is the number of ways to select k objects from a set of size n. Let's do an example. And what I want to compute in this example is 4 choose 2. So here I have a selection of 4 possible items, a set of size 4. I'm going to choose 2 of them. And how many ways can I do that? Well, we can think first I could choose the red spider. And then after I choose the red spider, since blue seems to want to come, I could choose the blue spider. But actually, if I choose the red one, I could choose any of these 3 after it. And that's something that's interesting to think about. So there are 3 things I could do after I decide to choose the red spider. I could choose the blue or the green or the yellow, which will be represented by orange for the purposes of my limited colors. So that's the number of ways I could choose the red guy. Now, it doesn't matter what order I take them in. This is about choice. So choosing blue and then red is the same as choosing red and then blue. So if I'm going to take the red to be one of my spiders, these are the 3 ways that I can do it. Otherwise, what's left over here, I don't get any more red spider. I can think of that as starting to give me a way to think about a recurrence relation or how to compute these things. So suppose I don't pick the red. I still get to pick 2 of these guys. Well, let's suppose I decide I definitely want to pick the blue spider. I have 2 options left for who the other spider is going to be. So I could pick my second spider to be the green spider, or I could pick my second spider to be the yellow spider. Now, those are the only ways that I could pick the blue spider. So remember, one way that I picked blue was over here, and the other 2 ways here. So there's still 3 ways that I could pick the blue spider, right? Now, what's left? Well, I've just got these guys left. So if I'm not picking red and I'm not picking blue, then I've got to take both of these. And so that gives me one option, green and yellow. So the number of ways that I can choose 2 items if I have 4 possible options is 6. And it's important to note how we got this number 6. This is not the same number 6 that we got when we lined up 3 objects in a linear order. This is a fundamentally different way to get the number 6. This is not 3 factorial. So what we want to think about is, how do we get this number 6, and how do we get a recurrence relation or a reasonable way to compute this in general? So here's our theorem that we're going to aim toward. Notice the difference between the definition, which is a combinatorial description, and the theorem, which gives us a way to compute it. So these are fundamentally different. This is a definition, this is a theorem. So in combinatorics, when we want to prove something and we have a denominator, usually what we're going to do is put the denominator on the other side so that what we get are 2 positive integers, and we'll try to do some combinatorics with that. The proof method that I want to use for this is I would like to do things by counting in 2 ways. That's something that we've seen before, and it's a tried and true method. So what are we going to count in 2 ways? I'm going to try to prove that I'm going to count k factorial, n choose k, and I want to write that as n times n minus 1 all the way down to n minus k plus 1. Okay, that's what I want to show. I want to show this. So maybe I'll put want to show, our standard shorthand. So I want to think combinatorially, well, what is that? What is this? So k factorial is the number of ways to arrange k things, and n choose k is the number of ways to pick k things. So I can think of this as the number of ways. So here, maybe I should emphasize that what I'm doing is the left-hand side first. I'm just going to think of what does it mean in terms of these sorts of definitions. And this one keeps rocking, so let's move that. So the left-hand side is the number of ways to choose k numbers from 1 to n, and then put them in a line. Okay, we choose the numbers and then we put them in a line. So for the right-hand side, I want to interpret the right-hand side as the same thing but done in a different way. In combinatorics, usually when we have a trigger word like then, it tells us that we could do it maybe in a different way. Is there a different order in which we could have done the same thing to get an outcome? So here we chose our objects and then we put them in a line. What if I just pick the objects and line them up as I go? So I do them sort of at once. I put them in a line as I go. So for the right-hand side, I choose the first number in n ways, right? And I'm putting it in line. It's the first number. And then I'm going to choose the second number in n minus 1 ways. And I'm going to continue down, and I'm only going to pick k numbers. So I'll choose the kth number in, well, this was n minus 0, so it's n minus k plus 1, n minus parentheses k minus 1 ways. These are the same thing. Either way, it's telling me that I'm going to, the two paradigms that I'm using here are, I could, in this thing, I would pick, I want red and blue spider, red before blue. In this paradigm, I would pick red spider first, blue spider next. It comes to the same choices, but it's just done in a different order and done in a different way. So I've counted the same thing in two different ways, and so these must be equal. And so that gives us this beautiful formula for computing the binomial coefficient in choose k.